let's open up to lesson 11.2. We are talking about entropy. So for the demonstration, let me ask you a couple of questions. So let's say you have an ice cube and you leave it on a table. Over time, it will naturally become it will naturally melt and become water. However, can this liquid water turn back into ice on its own? No, because that is not what can happen naturally. Same thing, your room. Let's say this is what your room looks like. It can naturally become messy. However, if you want to clean this, it doesn't clean on its own unless you put a significant amount of effort. So if you were to let nature clean your room on its own, it will never be clean because the amount of energy that you are spending in that process is none, and the amount of disorder that you will be left with as a result in your room will be a lot. So all of that mess is going to stay a mess. And that's because this is the natural way of things. So the aim for this lesson is, what do systems look like in nature? So as we saw in these two examples, it looks like nature prefers more disorder and things that require less energy. So systems in nature tend to have low energy and they tend to have high disorder. So we'll talk about both of these in this unit, but this lesson is about the disorder part, which we call entropy. This is the fancy word for disorder or randomness in a system. Disorder / randomness. So when we say that the entropy is high, then that means that there is more disorder. So the symbol for entropy that you are going to see is S. So let's look at different systems and how entropy compares for each one of them. So we're going to take a moment and draw the particle diagrams for a solid, a liquid, and a gas. So it doesn't specify what particles we have, so you can just draw a regular particle. So for solid, your particles are going to be closely packed together, and then in the liquid phase, they are going to be a bit more spread out, and then in the gas phase, they are going to be extremely spread out. So go ahead and make a prediction. How does entropy of the system change as the phase changes? So as we go from the solid phase to the liquid phase to the gas phase, what happens to entropy? Take a moment. So I hope we all said that the entropy is increasing as we are going from the solid phase to the liquid phase to the gas phase, and that's because the particles are spreading out more. So they are going to, if they are spreading out more, that means they are going to move more, and as they move more, they are going to be all over the place, especially in gases. So gases have the highest entropy compared to solids. And then we can also, I'm going to draw these lines to kind of indicate the movement. So as we know about gases, they move in random directions, they don't have a fixed direction that they go. So liquid particles also move, but relatively less compared to gases. So gases have the highest entropy. So, and that's because when we are changing phase, we are changing how the particles are arranged and how much space do they have in between them. So more space is equal to more motion, which results in higher disorder. So I'm just going to use the symbol S because now we know that the symbol for entropy is S. So now your next scenario is think about boiling water. So when water is boiling, it's going from the liquid phase to the gas phase. So what's happening to entropy? So I hope we all said that entropy is increasing because in liquid phase they are relatively closer together. In gas phase now they are very far away. So whenever you are asked to think of a phase change and how it relates to entropy, what you want to think about is what's happening to the particles. Are the particles moving closer or farther apart? So if particles are moving closer, then entropy is going to decrease because their movement will be less and less disorder. But if they are moving away, moving apart, then the entropy is going to increase. And then here's another one. So you are comparing a big chunk of a cookie and several smaller pieces. Think about which one do we think is going to have more entropy. So I hope we all said that the broken up pieces are going to have more entropy. And that's because every time you're comparing like one particle compared to multiple particles, more particles is always equal to more entropy because they are going to now interact with each other more, so like collide more, and then exert more pressure, and that's going to create more disorder. So more particles is equal to higher entropy. And then lastly, you're given these changes. Go ahead and take a moment to predict what is going to happen to the overall entropy. Will it increase or decrease? So for number one, we are going from the gas phase to the liquid phase. So particles are coming closer together. So this one is going to result in a decreased disorder, less entropy. In the next one, we are going from two ions and that are in the aqueous phase, and they're coming together to make a solid compound. So once again, the entropy is going down because particles were, when they were in the aqueous phase, they were moving around more, and when they're in the solid phase, now there's less movement, more order and arrangement. And in the last one, we have a compound and we are breaking that down into smaller particles. So one way to answer this is we can say we are going from one particle to two particles. So as we said earlier, more particles we have, the higher the entropy. And something else that we are going to record in this on the side is that when you're looking at chemical reactions, you can compare the number of moles. So on the reactant side here, you have 2 moles, and in the product side, you have 4 moles. So whenever you are comparing the entropy of reactants versus products in chemical reactions, the side with more moles is going to have a higher entropy. And there you go. That was your lesson on entropy. Pretty simple, pretty short, and I will see you in the next one.